Hello, everybody. So far, we have covered the formation of only one kind of star, a sun-like star with a solar mass equal to that of the sun, one solar mass. In this video, I want to address what about other masses? We have the stars that have lower mass than the sun, and we have stars that are much greater mass than the sun. Is the formation the same? Is it different? And how so? So let's go ahead and take a look at the formation of stars of different masses. All right, pulling up my slides. And we are off and running. So let's just jump right into it. For high and intermediate mass stars, and here I do need to differentiate and actually have the intermediate mass stars. So this is going to be the formation, the evolutionary tracks, tracking how a star moves on the HR diagram over time, and that time is its birth, its formation from a fragment molecular cloud fragment all the way to a main sequence star. And the evolutionary tracks for stars of different masses are shown here on this figure. And for the most part, uh, the high mass stars have a relatively simple evolutionary track. It's not like the complicated case where we had our one solar mass that had the Hayashi track and then the Henye track. Is for the high mass stars, it's pretty much just a beeline from low surface temperature to high surface temperature without a whole lot of change in luminosity, relatively constant luminosity. And these high mass stars will basically march almost directly to the left on the HR diagram to reach their place on the main sequence and be born as a main sequence star of high mass. So we don't have a Hayashi track for high mass stars. And you see that as you go to lower and lower mass, so here's a 15 solar mass, 5 solar mass, you do have a little bit of a downward dip before you just go over to the left. And by the time you're at a 2 solar mass, so now you're in the low mass stars, you start seeing the emergence, you start seeing a Hayashi track emerge. So the takeaway is that high mass stars form differently. They skip the Hayashi track. Uh, and also that the formation time for high mass stars is much, much, much quicker. With higher mass, gravity can pull everything together to go from protostar to star much more quickly. And I mentioned this in the previous video, but if you are curious, for the low mass stars, the sun-like stars and lower mass, we call those protostars while they're forming T-Tauri stars. For these higher mass stars, the ones that are going to end up becoming A or B type stars, those protostars have the name Herbig AE or BE stars. A Herbig AE star would be on its way to forming an A star. A Herbig BE star would be on its way to forming a B spectral class star. All right, so then that leaves the low mass stars. So for low mass stars, mass is less than 2.5 times the mass of the sun. The evolutionary tracks are very, very, very similar to our one solar mass case. They follow a Hayashi track. The only difference is for the really low mass stars, there's not really this Henye track. It's just all Hayashi track right to the main sequence. But that's a detail I don't expect you to remember for this class. So our lower mass stars follow a Hayashi track. They all look similar, but carve out a different space on the HR diagram. So you can see the 2 solar mass one, the Hayashi track is not exactly the same as, say, a 1 solar mass. But overall, they're the same, or they're mostly the same. We are seeing these Hayashi tracks. And since we are talking about protostars on a Hayashi track, we call these ones T-Tauri stars when they're in their protostar phase. And the lower the mass, the longer the formation. So in summary, one of the big takeaways I want you to have from this is that the formation, the evolutionary tracks differ based on mass. And one of the biggest differences is that the higher the mass, the faster they form, and the lower the mass, the slower they form. To the point where this 15 solar mass star forms very, very quickly, while this 0.5 solar mass star takes a very long time to form. And now we have to take a step back. We have talked about the formation of different stars, or stars of different masses, but we haven't answered a really fundamental question. If we have, say, if we look at a galaxy and we see a whole bunch of stars forming in all their star forming regions, what would the balance of how many stars of each mass are formed? So how many low mass stars, like M-type stars, do you form compared to, say, Sun-like G-type stars, compared to, say, your O and your B stars? And this is actually a very active area of research where we're still trying to nail down exactly how many of each massive star is formed. And we try to encapsulate this with what's called the initial mass function. So imagine all the stars in the universe form at the exact same time. What would the distribution of their masses be? How many high mass stars do you have to how many low mass stars? And that's what this image is showing over here. Notice that the x-axis is a logarithmic one, but it's mass. So we have our low mass over here, we have our high mass, and yes, this is in solar masses. So here you have your B-type stars. And here you have your M-type stars. And here you have your Sun-like G-type star. And over here, on the y-axis is just the relative number. How many of, say, low mass stars do you have compared to how many high or sun-like stars compared to how many high mass stars? We call this the initial mass function. It's a pretty complicated thing, and there's a lot of details that are buried in this that are well beyond the scope of this course. But I want to go ahead and give you the generals because this is going to dictate how many of each type of star forms, which will dictate how quickly we enrich the galaxy, a galaxy or a universe or a local area in a galaxy and heavier elements, how many stars are going to be going supernova, how many are becoming planetary nebula. It is a crucial part to understanding the evolution of galaxies on a whole. And it's just darn interesting to think about. Oh, no, that we can start nailing down how many of each massive star to form. So just because it's a little bit of a tricky concept, the initial mass function, usually just called the IMF. It gives how many one solar mass stars to expect relative to the number of half solar mass, to 1/10 of a solar mass, compared to how many are 2 times the mass of the sun, 20 times the mass of the sun, so on and so forth. And the takeaway is that you form many more low mass stars. You form a lot more low mass stars compared to high mass stars. A relative high number of low mass stars, a relative low number of high mass stars. And to really nail this down, for every 1,000 sun-like stars, one solar mass stars that you form, you will only form a single 10 solar mass star. So for every one B-type star that you form, you'll form 1,000 sun-like stars. That's a pretty stark difference. And you'll form even more M-type stars. Now, a very active area of research is still trying to figure out this low mass end, because the lower the mass, the dimmer the star, the harder they are to find. So actually nailing down all the details of this are pretty difficult, but we are getting better. Even though it says that we don't know this part of the IMF very well yet, we are getting better day by day. And a lot of that is coming in as we really start to discover and appreciate how important a non-star, a failed star, called a brown dwarf, how prevalent they are out there in the Milky Way and in the universe in general. Because if we're forming, we have our giant molecular cloud, is going to fragment into, say, dozens to thousands of small fragments that can become stars. And you form a lot more low mass stuff than high mass stuff. And we're trying to, you only become a star if you have enough mass to drive the core temperatures up to that 10 million Kelvin required to start the proton-proton chain. What happens if you have a fragment that's collapsing, but it just doesn't have enough mass for the core of that star to ever get hot enough to start the proton-proton chain? If you don't start fusion in the core of the object, that object is not a star. And we call these objects that don't have enough mass to ever start fusion in their core brown dwarfs. So a brown dwarf, you can think of it as a failed star, although it's just another object in the universe. It didn't fail at anything. It's just a thing that exists. So a brown dwarf would be a star, or we'll go ahead and call it a star, that does not have enough mass to have hydrogen fusion ever start in its core. So perhaps I should say a non-star but a celestial object that's very interesting unto itself. This is going to be the very low mass end of our IMF. How many dwarfs are there out there? So, what is the mass requirement? Because now we have this weird category of what's the difference between a planet like Jupiter that's made out of hydrogen and helium and a brown dwarf that's made out of hydrogen and helium. What's the difference between a planet and one of these brown dwarfs, a gas giant planet and a brown dwarf? And we actually do have rough boundaries. We do have a delineation between what is a gas giant planet and what is a brown dwarf. One, a brown dwarf can form in isolation. You can't form a Jupiter planet in isolation. But even more so, there are mass requirements that correlate to something physical happening in the star. So the mass requirement to be a star, and in other words, to reach core temperatures, to kick off that proton-proton chain, to reach a core temperature of 10 million Kelvin, the total amount of mass for that object needs to be about 8% the mass of the sun, 0.08 solar masses. And now you might see why that pretty much every time I've shown mass, it's always at about 0.1 solar masses is the low end, because that is about the requirement to be a star. If you're curious, that is about 80 times the mass of Jupiter. So if you ever hear people refer to Jupiter as a failed star, they're way off the mark. You need 80 Jupiters all combined together for Jupiter to be a star, not even close to a failed star. It is a gas giant planet. However, objects that are 12 to 13 times the mass of Jupiter, that's significantly more massive than Jupiter, they will have a very brief moment of fusion happening in their core. But it's not the proton-proton chain that's fusing hydrogen into helium. It's just one of the parts of the proton-proton chain where they can fuse deuterium into, say, helium-3. So they can fuse heavy hydrogen, or they can bring hydrogen atoms to form heavy hydrogen. So this deuterium fusion, mostly fusing deuterium into, say, helium-3, is very, very short-lived because there's just not a lot of deuterium in these objects. And it never gets hot enough to actually establish the proton-proton chain, which can sustain a star's life. It can power a star for, in this case, very low mass, trillions of years. That just doesn't happen. But you will have a different kind of fusion, deuterium fusion, for objects that are about 12 to 13 times the mass of Jupiter. And that gives us a range for these brown dwarfs. A brown dwarf would be anything that is large enough to have this brief period of deuterium fusion, but small enough that it never actually establishes the proton-proton chain in its core. Its core never reaches 10 million Kelvin, which gives us a range of 12 to about 80 times the mass of Jupiter. And it's easiest to do these in Jupiter masses instead of the masses of the sun. For reference, the mass of Jupiter is about 1/1000th that of the sun. If you're smaller than this range, you're a planet. If you're larger, then you're a star. So these things are incredibly difficult to find. And one of the reasons is they don't have fusion going on. They're not generating their own light via fusion. So the only way that they are radiating is from that gravitational collapse of the fragment and squeezing everything down into a small spherical object, that conversion of gravitational potential energy to heat. So that leftover heat from its formation, that's a lot of energy, but that's the only energy it has, and it will radiate that out to space, and it'll be forever cooling down. But this is the only primary source of energy that these brown dwarfs have. They're not producing their own light via fusion, which means that they're not going to be very bright. They're dim. They're very, very intrinsically faint. You could use the Stefan Boltzmann's law to realize that they're not giving off much light at all. They have a very low luminosity. Plus, they're incredibly small, which isn't working out very well for them either. So these things are very, very hard to detect. Theoretically, they're predicted, but how many of them actually exist? How can we confirm? How can we sample that part of the IMF? So if we want to look for them, their peak is going to be in the infrared. So we should probably use infrared-based telescopes. Or what we should do, since stars like to form in binary systems, look for a brown dwarf in a binary system, because the star and then the brown dwarf would be in orbit around one another, which means that sometimes the star would be moving towards us and away from us, which means we can look for the Doppler shifts. And if they're periodic, then we can go ahead and determine that there's something else there. We can do a quick estimate of its mass to determine that, hey, look, it's a brown dwarf. So we predict that there should be lots of brown dwarfs out there. And until very recently, we had only discovered hundreds of them, and that number remains about the same. We're probably up into about the thousands now. But we had estimated, based on our knowledge of the IMF, that there should be 100 billion or more of these in the Milky Way itself. So how many are really out there, and how can we actually go about getting this? And I do want to show you that these things exist. So here are some direct images of brown dwarfs. So this is Gliese 623. This is a very large brown dwarf. It's almost a star, so 80 times the mass of Jupiter. And this is Gliese 229, another brown dwarf. Boop, right there. That's about 50 times the mass of Jupiter. So we can observe these things. And if we can observe them, then we can take a spectrum of them, which means that we can come up with a spectral classification for them. And now we can put our brown dwarfs, we can assign them a spectral class. So originally we have the star spectral classes, O, B, A, F, G, K, and M, from hot to cool. But now we can add brown dwarf spectral classes, L, T, and Y. Most L's, early L's, are certainly stars. Late L's are arguably stars or brown dwarfs. They're about like Gliese 623, where they're right at that mass limit. But we didn't discover the L class of star, the L-type stars, until we started to do this dedicated hunt for our brown dwarfs. And here we have, so we have the L types, and now we have the brown dwarf types, the T and Ys. So adjust your sorry about that. Adjust your mnemonic as you would like for remembering your spectral classes, or I don't really test you on the T and Y being the brown dwarf spectral classes, so don't worry about it too much. And I want to end this video by showing you we've made some significant progress. So here is a star cluster. This star cluster is RCW38, a very creative name. And this is being observed with the Very Large Telescope, the VLT, with the NACO instrument, which uses some of the most advanced adaptive optics. So we can see the stars individually, and it's a very, very sensitive telescope. So we can see very, very faint things, ideal for hunting for brown dwarfs. And it's just looking at this star cluster, an ideal place to try to sample the IMF, because you have a whole bunch of newly formed stars. So if you look, hey, that's the IMF. And here we're zooming in on these objects that appear to be everywhere. And each one of these arrows is pointing out a brown dwarf. So based on these images and counting and knowing statistics, it's estimated that there are about half as many brown dwarfs as there are stars in this cluster. That gives us a data point on the IMF. And then we can extrapolate that, since now we have a new data point on the IMF. And that suggests there are about 25 to 100 billion brown dwarfs in the Milky Way galaxy alone. So these brown dwarfs, sure, they're hard to see, but they are numerous and they are everywhere. Okay, pretty exciting little video. I hope you learned a whole lot, and you know an entirely new celestial object that you probably didn't know anything about before, the brown dwarf. I will see you in the next video.